So today we have the second lecture from Luc, going more into the details of the phenomenology of the Feebly Interacting Particles. So Luc,
thanks a lot.
In your hands.
Okay, so thanks a lot, and thanks for the one who joined us for the second lecture today. So let me just share my screen first. Okay, there we go. Okay, so can you see it properly? Yes?
Yeah, perfectly.
So, so this is the second lecture we're going to have about trying to find the invisible, meaning studying light but hidden sectors beyond the standard model. So in the first lecture, we went through a bit of the theoretical tools that we can use to describe these types of objects and how we can apply them to derive some constraints from collider physics. So we'll try in the second set of lecture in our 2 hours to delve a bit more into two, let's say, phenomenological topics on this object. The first thing will be the relink with dark matter. So we'll mostly spend an hour on that before the break, trying to understand a bit how and what are the link between these feebly interacting particles, or FIPs for short, and dark matter. So this will be the first part, and we'll try to spend some time on it. And then I'll try to finish these lectures by going a bit more into the low mass physics, so the low energy physics, and how we can use this kind of feebly interacting particle to look for a set of different anomalies. Okay, so maybe I should start very briefly by some reminder of what was in the last lectures on this. So what I call feebly interacting particle, this could be very loosely defined as being this new neutral particle which interact with the standard model via the suppressed interaction. So as we have seen in the first lecture, those objects are interesting because they're a bit at the crossroads on many of the biggest problems of the standard model, and at the same time have amazing experimental prospects because they are testable in a very broad range of experimental setups. So going from flavor to dark matter, to neutrino physics, and all the way up to the LHC for long-lived and displaced particle vertices. So what we saw during the first lecture was that it was very useful to try to parameterize the interaction between the feebly interacting particle and the standard model via what was called this portal operator. So basically objects made from standard model fields in such a way that they were gauge singlets. And this was the case because we wanted, of course, that any feebly interacting particle should not interact via the standard model gauge groups. And so we've seen that basically the scalar portal was just a Higgs square that we could match it up to the Higgs, and that would link eventually to some mixing parameter between the Higgs and the dark Higgs. We could do the same thing between the photon and what is called the dark photon, triggering some kind of kinetic mixing that we've seen that after rotation gives you a tiny interaction between the dark photon and the electromagnetic current. And then we went on to the neutrino portal, and finally what I would call the fermion portal, in which you just plug together two fermions in the standard model, and which can then be matched together with either two fermions from the dark sector, or an ALP, or even a new gauge scalar fields. So building all together, the interesting bits I would say now is that not only this kind of objects theoretically quite appealing because the construction are quite simple, they are also at the crossroad of many, many anomalies. So I just made a very tiny list, which does not mean to be completely exhaustive on the things, for which some of the anomalies could be linked somehow to the presence of light particles. So we have a significant amount of astrophysical ones, of course, from detection in xenon to Hubble rate tension with very strange and very light objects, the dark no small scale problem, we'll come back to that in a second, some stellar cooling hints, which come and go, and which are usually linked to axion particles, and also even some possible models in the low primordial abundance of lithium. So, of course, this is from the astrophysics. We have also a range of observables in precision neutrino experiments, ranging from the proton charge radius all the way up to sterile neutrino in the mini-Boone excess, for instance. And then covering also flavor objects from the CKM to the high energy. And I'm sorry, I just recognized that some of it is still in French. So this is a very broad picture. And in practice, what we're going to do in this lecture is try to talk a bit more about astrophysics and how we can use FIPs for dark matter. And then we'll try to touch a bit about this kind of other precision neutrino experiments and flavor issues. Okay, so I guess we have to start now. So let's start by maybe one very simple diagram, which is the feebly interacting particle and its link with dark matter. So the most basic thing I want to put forward here is this very simple diagram. Now this represents in the early universe how dark matter particle can annihilate via the exchange of a mediator, this V, into standard model particle. Now this is a cornerstone of the standard WIMP paradigm and more generically what is called thermal freeze out. So you want to put the dark matter into thermal equilibrium with the standard model bath, and then you start with a mechanism to actually annihilate it in the early universe. Okay, so the nice part is that now it's the time to actually explain the green light line that I've shown you before in the first talk. So if you remember, this was like a very generic plot of what was known in particle physics. From the TV all the way down to the EV with different types of constraints, showed again. And so you saw that I put at the time this kind of dark matter freeze out line here, which would go all the way up to the TV, and that somehow would just cross and go down there. So my goal in this first part of the lecture will try to first make you understand a bit why this dark matter line into this way, and why when you are in this region, what you really need is a Feebly interacting particle to mediate the decay. So maybe here it's good to take a step back first and realize why are we interested at all into looking for a new light dark matter particle. Well, the truth is that we've made absolutely amazing progress on the experimental side, looking for a WIMP. So this is the standard plot that you've seen hundreds of times already. You put the cross-section for the scattering dark matter with nucleon, the same for its mass here, and then you look at where are the direct detection constraints pushing by. So these are some of the neutrino limits. And so what we know is that basically we're in a very mature area of research where we had a lot of very well-developed experimental program which have been able to push by orders of magnitudes where we can think the dark matter is. So the main question about light dark matter, which started mostly a decade ago, I would say, was whether or not we could make it work in the places where those limits were not that stringent. But there's a very good reason for that. It's all of those kind of objects assume that the dark matter is non-relativistic. And so if you want it, for instance, to scatter on, let's say, an argon nuclei or a xenon nuclei, even worse, then it means that this particle needs to be very massive, or at least massive enough so that it can leave a scattering signature. If you weigh too small in mass, you'll never be able to actually scatter and transmit some energy into your nuclei, and so therefore you'll not be able to see a signal in your direct detection experiment. So actually going down in mass in dark matter implies that these direct detection experiments, as they were designed to search for the WIMP, will not apply directly. So that means two things. First of all, we need to ask the question, okay, theoretically speaking, can we build a dark matter model which shares most of the very good aspect of the weakly interacting massive particles, so thermal freeze out, very simple calculation, and so on and so forth. And then, of course, on the experimental side, what can we do to probe this kind of objects? Okay, so what I suggest we do now, just for a short while, is to try to make a very small tabletop relic density estimate. So the idea is that we'll try to build and understand why we need a Feebly interacting particle to get our dark matter below the GeV, and also some of the constraints that are present on this kind of object. Okay, so let me think. Yes, does that work for you or not?
Yeah, we can see.
Yes, okay. Can you see the, no, wait, the thing is not updating, I think. No, it is. Okay. Oops. Wait, let me try to share it again because it seems that it's not updating properly now. Oops, sorry about that. Let me just share it again once more. I'm at home, so I had to do with what I had. This is extremely sad.
No worries.
Try to see if we can connect it again. Oops. Okay, very good. Zoop, zoop, zoop. I think the USB cable I was using is not that good. Okay. So the plan is to look for your very first basically light dark matter model. So the idea is that we want, yes, now it works. So we want to estimate the relic density, which would come from the thermal freeze out of this kind of relics. So the relic density, from something like the diagram I showed you before, meaning that you have, let's say, one chi, a chi bar. So you have, for instance, a Dirac fermion, which in the early universe will annihilate from the exchange of one of those light mediators we've seen before into, for instance, electrons. So we'll take chi, a Dirac fermion. And for now on, we'll not really specify what is V. So V is just a mediator. It will have an interaction both with the dark matter, an interaction G chi, and another interaction with the electrons GE. So at that stage, we don't have to really specify what those couplings are, and we want to let dark matter tells us what range of coupling is viable. So how do we do that? So the first thing is, of course, we need the thermal average of the annihilation cross-section. So we need these objects. So we need something which is written like that. Oops. Where we have what? V is the relative velocity. So this is pretty standard dark matter lecture, so I will try to go a bit fast. Oops. Between chi and chi bar. Oops. So V is given by the square root of the Kalen function from the initial state, divided by the scalar product of my initial momentum. So here we'll take that chi as a momentum, pi 1. This is P1, this is P2. Then this guy here will be K1, this will be K2. So from that, what do we get? Well, the first idea is that, so we'll stick with the Kalen function for the initial state. So you remember this is a triangular function. So the differences between these two objects. Divided by, then in the non-relativistic regime, the scalar product of P1 and P2 is very easy to calculate. It's simply twice the mass of the object. So this is because we're interested into the annihilation of dark matter by the time that it's not relativistic anymore. This is a standard thermal freeze-out mechanism. You're interested in what happens when the dark matter becomes non-relativistic. So if we get this object, then it's pretty easy to find the actual cross-section out of it. Oops, times V. Before taking the thermal average. Okay, so we have a factor of 30 pi for the phase space. Then we multiply by the square root of the Kalen function on the initial object. The same for the final object. We have to average by the initial helicities. So these are two fermions. So this is 2 by 2. And then we have, of course, the sum over the amplitudes. So we have to sum over the helicity of the final states and the amplitudes for the process. To that, we have to multiply again my V, which is written just here. Oops, sorry. This is the final. Oops, you can correct me if you see that I made a mistake along the way. Oops, this is a final one, and this is the initial one. Okay, this is time square root of in divided by 2m chi squared. Do you know what is the Kalen function, right? Or do you want me to remind it? Yes? No?
For me, it's okay.
Okay, so then I'll go on for that. So there's a standard function that you have in kinematics for 2 by 2 and 1 to 3. You can define it, let's say something like this, A, B, C. This is A minus B minus C square minus 4BC. The simplest way ever to actually write it down, and there is more symmetric formulation, but that's more or less the same idea. Funnily enough, this is actually related. It's called triangle function also because it's also related to the actual area of a triangle with a given length of the. So if you give me A, B, C, you can try to construct a triangle from these lenses, and then the Kalen function will be linked to the actual area of the triangle.
Okay. That I didn't know.
See, learned something. Okay, so to get something done here, we of course need to estimate the amplitudes for the process I showed you just before. This one on my screen yet. So what do we have? Well, we have the product of J chi, J e, which are the two couplings of my object. And then what do we have? We'll have a V bar P2, because we'll have now two Dirac fermions, another one here for P1. And then we'll make an assumption that we are in the regime where MV is much bigger than M chi. So basically the mediator is heavier than the dark matter. And of course, this is also much bigger than the temperature of freeze out, meaning that the typical impulsion, the typical form momentum of the particle involved will be much smaller than the mass of the V and the one of the chi. I tell you all of that because this allows me to basically replace the hard propagator that would be inside the unitary gauge by just 1 over MV to the fourth, simply because we're in an effective theory here where we can integrate out the heavy V. So the propagator just picks up this contribution, and then you have the same thing for K1, gamma nu, and then you have a V, K2. Okay. So if you put everything together there, you have just a bit of Dirac algebra to do, and I will spare you the Dirac algebra, which is slightly more annoying. That's the one that we're going to do afterwards. In that case, we just have to square the amplitudes and try to derive what we have. So basically what is interesting is that we'll get the couplings to the square. That's logical. We'll have also 1 over the MV here. Sorry, this is a square. Yes. So we square it, it goes to the fourth. And then we have some dependency about cosinus theta, which is the angle between the initial and the final state in the center of mass. Oops, there is a 3 here, and you have an m chi square, which arises. Okay, so I mean, these are just basic calculation of Dirac algebra, so it's not particularly illuminating. You can just integrate this whole thing here on the cos theta, and that gives you 32. So altogether, the actual numbers here are not very illuminating. What is very interesting is the scaling of this full cross section, because if you put everything together now, so together we get what? We get that sigma v, which is the relative velocity of my 2 dark matter particle times the cross section, is given by 1 over 8 pi. This is because I get all the factor of 32 together. And then you have the couplings here squared times what? Times the mass of my dark matter particle divided by mv to the fourth. This is very important. So we can see many things from this expression. The first thing is that it's constant in V. So it does not depend on V in first approximation. So there is no dependence in V. This is what we call an S-wave process. An S-wave process means that basically the dark matter annihilation will not depend on the velocity of the true dark matter particle. So whatever the velocity, you always manage to annihilate those two objects. So this is very important. This is a good thing for the calculation because it means that the thermal average is trivial to take now because this object is basically constant over the thermal average when you are at very low temperature. On the other hand, this is catastrophic for the CMB. So we'll discuss that a bit later on. But basically, this means that your particle of dark matter will be able to annihilate as efficiently by the time of the CMB or even later on, I mean, currently, that they are at the time of the decoupling. So this is something that is typical for the WIMP, but as you're going to see, if you want a dark matter below the GV, this is something that you will want to avoid. So we will want to avoid such S-wave process. So we'll come back to that and I'll show you some of it. This is something that is quite easy to do on the theoretical side, but that you need to take into account. But the second thing is, like, once we have that, we can try to see what is the actual relic density. So, whoops. So after the standard density, the standard relic density estimate for freeze out. So at that stage, you remember this is what you get from freeze out. So you have the cross section, you requires it to decouple. So you want to calculate when the rate for annihilation is equal to the Hubble rate. And once you do that, you're able to basically link the final relic density of my dark matter, something that I give you exactly here, as a function of the decoupling temperature, which is written in terms of this X parameter that you surely know from the WIMP. So this object is given by the mass of your dark matter divided by the temperature of decoupling. And then you have the number of effective degrees of freedom in your theory, which depends on basically what is present in the thermal bath, the measurements of how much particles you have available in the thermal bath. These are all order 1 factors, so it's not very important. The most important one here is the cross section, GV minus 2 divided by sigma V. So this is our target. So now that we've just estimated sigma V, we can try to look for comparison with this target 4 × 10⁻⁹ and see when we can reach this target. So we get, replacing now my cross section, we just want that the couplings to the chi, the couplings to the E divided by 8 pi, times the mass of my dark matter particle divided by mv to the fourth is equal to 4 × 10⁻⁹ GeV minus 2. So we learn a lot from there, right? Because first of all, okay, let me just take the square, and then we have GE, and we divide that by mv square times m chi, and then this is just 3 × 10⁻⁴. So from this extremely simple calculation, we can already rederive plenty of things. We can rederive the standard limits from unitarity, from dark matter, that we'll come back to a second, the Lee-Weinberg limits on where a FIP can go in terms of mass, and as we're going to see, the typical size of the couplings require to my mediator so that I can get my relic density at low mass. So the first thing is, let's try to get the window for thermal freeze-out dark matter based on this expression. So the first thing we want to do, based on this expression, So the first thing we want to do is try to assume that, let's say, the couplings are as big as possible. So we want to put ourselves into a situation where all of those guys are extremely massive. This is like the right-handed side of the WIMP, and it's not at all in the region of what you get for the Feebly interacting particle. So if you take, for instance, what is called the unitarity limit, we'll come back to that, for the couplings, meaning that each coupling is taken, GE, G chi is taken something like square root of 4 pi. What you get is that you can replace into this expression, you take m chi of the order of mv to make sure that you have no suppression from the propagator. And then you imply that typically m chi has to be smaller than tens of TeV. You see, this is quite easy to see from this expression here. This was GeV minus 1. Oops. So you just have to invert it. You see that you're typically around the TeV scale there. So if your couplings are bigger, you are able to push it a bit more, let's say to the tens of TeV. So this is the first limit. Oops. This is the unitarity limit, and it tells you that typically in a normal and standard cosmological history, you cannot have something which realizes the thermal density via freeze-out using this kind of diagram significantly above the tens of TeV regime. So that's the first limit for the dark matter. Now, of course, you're interested a bit more into what happens in the low mass regime, because, well, this is a lecture about Feebly interacting particle. So now suppose that the mediator is something that we know, meaning that it's not a new particle. For instance, it's a Z boson. So if you have now MV of the order of MZ, which is typically 100 GeV, then it means that you are in a situation where if you get this thing here, you see that you put MV into the other side and you are somewhere around the GeV minus 1. Because this MV is now 100 of GeV, so you can set it here. And so altogether, if you have MV equal MZ, and then you suppose that basically the coupling to the E and the coupling to the chi are given by something like the weak interaction at 0.7, you get M, which is roughly bigger than a few GeV. This is very important. It tells you that if you have a mediator here, this V, which is typically of the electroweak scale, meaning hundreds of GeV, you cannot have a dark matter particle which is lighter than few GeV. This is sometimes called the Lee-Weinberg bound. So this tells you that if you want a dark matter below this scale, you need another mediator, something that is not the Z, something that is not one of the electroweak gauge bosons. So, yes, that was the other one. And then the last one that we want to do now is suppose again that MV is now of the order of M chi, but then both are very light. And then we wonder, okay, what is the typical scale of my couplings so that I can get my dark matter? So I will take the interaction with the dark sector of order 1. And then if you do that, you get something of the order. So M chi divided by MV square is of the order of 0.3 GE over 10 to the minus 3 GeV minus 1. So altogether, it means that if you use this kind of thing, having a sub-GeV dark matter requires two things that will come back later on. First, a new mediator, something that can interact with the dark sector and with the standard model, which is not an electroweak gauge boson, and tiny couplings to the standard model particles. Now, this last requirement is extremely important, right? Because if you remember for the first lecture, if the particle is very light, then it means that it's very easy to see, and so you need to hide it. What is absolutely remarkable is that having a particle below the GeV requires, in order to get the relic density, coupling of the order of 10 to the minus 3. So if we come back to that, oops, this is a plot I showed you last time of all the constraints we have on a dark photon. So we went to all of those constraints together, but what you typically see is that you are in the 10 to the minus 3-ish regime for the couplings. So the dark matter very rough estimate that we made pulls you here, which means that basically making a tabletop calculation of what is the typical strength of coupling you require for sub-GeV dark matter precisely send you to the limit where you can hope to see that in the near future, which is of course part of the very interesting feature of these types of objects. Okay, so last thing I want to show you before we move to the slides part of the presentation for this dark matter is a funny comment about the density of dark matter. So, okay, the local density of dark matter, oops, can someone actually knows what it is? No, I'm sure Corinne knows, but yeah.
No idea for me.
So the common relic density of dark matter, you can get it typically between 0.2, 0.4, and then this is given in GeV per centimeter minus 3. Now, what is very important, of course, is that we can only have access to the mass density, right? Because after all, this is what will drive, well, the gravitational fields around us. So we cannot know very for sure, but this is more or less where we expect it to be. Now, if it's a WIMP, how many WIMP do we expect as a number density around our local dark matter halo? So the number density is simply given by, well, this mass density divided by the mass. So typically you can count on being something below the dark matter times centimeter minus 3. So let's see. If you're in a situation where the dark matter is below the GeV, it means that you typically have like one particle of dark matter per centimeter cube, which is quite nice. I mean, if you actually look in this tiny centimeter cube here, you have already one dark matter in it all the time. This is much, of course, bigger than in the case of the WIMP. If you take the WIMP, let's say at 1 TeV, then you are in 10 to the minus 3 centimeter cube. So I mean, it means that you have to take a 10 over 10 box to be able to get one dark matter particle. But now keep in mind that if you go to much lower masses, so typically we'll see some dark matter models in which you have MChi of the order of 0.1 MeV, for instance, then of course it means that you have 4,000 particles per centimeter minus 3. If you just want to get like an idea of how much this is, you can just consider and compare with the LHC vacuum. So the LHC vacuum is one of the best vacuums, I think, that we have around, at least on Earth. It's at 10 to the minus 14 bar, which is really not much. But of course, you have to multiply that by some Avogadro numbers. So the number of particles of, let's say, air objects that you can still find in the LHC is of the order of 10 to the 5 centimeter minus 3. So basically, even if the pressure is extremely low, in LHC per centimeter cube, you still have something like 100,000 particles, which is still incredibly good compared to an actual mod of 10 to the 23. But you see that in the LHC tunnel, if you had like a dark matter of the, let's say 0.1 MeV, you'll get a percent level dark matter compared to what you have. So there's almost as much dark matter in the LHC tunnel that's actual matter in it. It's even worse if you look for some very light dark matter that I will not touch too much, which is axion dark matter. So here, typically, you want something which is at the 100 of micro electron volts. So that means that the numbers, if you plug it back into this formula from above, are huge. I mean, we are talking something like 4 10 to the 12 centimeter minus 3. So in 1 centimeter, around that, you have something like 1,000 billions of axion dark matter. So what this means is that if you are looking for light dark matter objects, and that the signal does not depend on the mass of your particle, then the lighter you go, the more chance you have to see something. simply because you have more density of particles around than you have for a WIMP. This is a reason why they could look at haloscopes for axions, for instance. Because for very light particle, if the axion is a dark matter object, then you expect crazy density numbers of axions per centimeter cubes. So there's something to keep in mind. The relic density of dark matter fixes the mass density of the object, at least in the local halo. So the lighter you get in dark matter mass, the more particles there will be lying around. And so in particular, you see that if the annihilation of my particles do not depend at all on their velocity, for instance, then the lighter you go, the more interaction I should have. And so you end up in a situation where typically, and we will come back to that, the lighter the dark matter model, the more interaction you may have, and so therefore you must often find a way of suppressing this interaction at low velocity. Okay, so let me come back now for some slides in that part. Okay. So what did we learn from this pretty simple approach? So we made a very simple assumption of what could be the dark matter, and we found out that there were different regimes, and that if we wanted to go below the GeV, we needed a new mediator. So let's try to summarize a bit all that we had. So this is a very standard plot that you surely have seen already about like where is dark matter. So we've just seen from a very simple back of the envelope calculation that typically if you're a WIMP, or for all that matter, if you're a thermal dark matter candidate, which comes from freeze out, you cannot be significantly heavier than the GeV. This is just because then your annihilation cross-section falls off too fast. So typically you see that this is this WIMP window, and then around the tens of GeV you hit the Lee-Weinberg bound. So basically a WIMP is typically constrained by the unitarity of its interaction on the left, the Lee-Weinberg bound on the right, the Lee-Weinberg bound on the left, and some other constraint, which is the CMB constraints, meaning that, as I discussed, the lighter the particle dark matter, the more objects you'll have in terms of density. And so therefore, the more production you actually expect to see. So putting these two things together, you see that at one point you start having too many interactions. And so if you don't suppress this kind of interaction one way or the other, when the dark matter is non-relativistic, or at least very cold, then you'll get some trouble because you'll start injecting ionizing particle at late time. And this is a problem because CMB is very precisely measured. You can do also the same thing with indirect detection, because if the dark matter gets very light, then again, you have a lot of particles around, and so indirect detection gets better and better. But they can see more and more signal because you have more and more interaction in terms of density. So this first set of limits, meaning how can we go below this GeV, tens of GeV range, can be bypassed by two things. First of all, a new mediator, as we saw. And second, making sure that the dark matter interaction are very suppressed at late time. So another range of way to do that, the first possibility is to go P-wave, meaning that the annihilation of dark matter will come proportional to the velocity. Another possibility, and I mean there are many of those, is to go through co-annihilation. So I'll come back to one of those mechanisms, co-annihilation, in the next slides, where I'll try to actually build with you some explicit models. So, okay, now that we've reached, let's say, breached this limit of the 10 GeV, we enter the realm of sub-GeV dark matter. Then the next wall is what happens when you reach the MeV. So between roughly 1 MeV and 10 GeV, you can use the annihilation cross-section that we calculated together, and you can see that, okay, you need a mediator with a tiny couplings. Once you reach the MeV, something pretty annoying starts to occur, is that the dark matter annihilation occurs at a time where we start to know the universe very well. And this is because this is a time where we have big bond nucleosynthesis, which starts to kick in, where the neutrino decouples also. And so if you put everything together, it's actually pretty hard to push your dark matter much below the MeV, at least the tens of MeV range, because if it freeze out, it will freeze out at a temperature which is like 1/30 or 1/20th of its mass, which will start to reach basically the time of BBM. So this is like a summary of some of the constraints that you could have from a dark matter which would interact mostly with electrons, a bit like what we've constructed together. So what you see here is that you have limits from both BBN, basically preventing you to go to too low mass, because there you would destroy all the nucleosynthesis that you've made because you start putting very high energetic particles. And then you have limits from Planck, which is from the effective number of neutrinos, which basically just tells you that you're pushing entropy into the thermal bath at a time where you should not. And this is very important because this entropy will then be used to calculate between the temperature of the different baths what will be the shape of the oscillation of the CMB. So this is a bit hard to do, basically. It means that as soon as you reach below the MEV or at the MEV, you'll start getting into troubles, let's say, with the very well-known cosmology. Something that, of course, do not occur at all around the 10 GeV range, where we don't know much. So this can be partially bypassed, and this will be an example by the end of this part about dark matter. If you can have some non-trivial neutrino interaction, for instance, so that you would try to make sure that the number of the effective number of neutrinos is compensated in a certain way, or to make sure that the dark matter is not in thermal contact anymore. So we'll come back to that because those models of freezing are quite important, in particular for experiments looking at very light dark matters. The last bit is that even if you manage to go through this MEV regime and actually design a dark matter particle which would work below this, you finally end up with the regime of what is often called warm dark matter. So there the idea is that once you start having a dark matter with masses in the tens of keV regime, by the time of structure formation, the early universe, it will still pack quite a lot of kinetic energy, meaning that it can actually stream out of the gravitational wells, and that will prevent you from actually constructing small structures. So this is very important because it's a regime in which we may actually hope in the next future to actually measure something about dark matter itself. So with like the Vera Rubin Observatory, for instance, we could hope to actually measure more and more of these halos. And once we know about the, let's say, small scale structure of the universe, this can tell us a bit about the actual structure of what is dark matter, basically. Okay, so, but we'll never really reach this limits in the models that I have here. Typically, we'll see that we'll go at least up to tens of keV, much below that. I just want to mention before all of that, that of course here I'm not talking about what I would call ultralight dark matter, which is a completely different regime altogether. For instance, for the axions, when you have objects at the microelectrovolt. There, everything is completely different because you have very long wavelengths and different production mechanism and so on and so forth. Okay, so let's see, how much time do we have on this part here? Okay, 42, perfect. So let me finish this part of dark matter by presenting you some explicit construction of light sub-GeV dark matter models, and some of the reasons why we can, basically how we can study them and what are the predictions in terms of detections. So as we've seen before, if you want to get thermal freeze out with sub-GeV dark matter, you need a new mediator. So this is very important because it tells you that basically, from my experience, most Feebly interacting particle models can be embedded one way or the other into a light dark matter setup. This is with various levels of complexity. I mean, the dark photon model that we showed before is extremely easy and is everyone's favorite, basically. But basically, any Feebly interacting particle models you can play out more or less in certain part of the parameter space. You can transform it into a light dark matter setup. Because a Feebly interacting particle paradigm is exactly what you need for the mediator in the annihilation here. So, okay, this is more or less what we estimated before. We get the proper relic density when those objects are in the hundreds of MeV range and with some tiny kinetic mixing, which puts us just out of reach of current experimental constraints. So what is important to keep in mind is that this, I will present just you two models. There is an extremely large number of models which have been designed. The main part is that once you actually acknowledge that you need a new mediator, it means that you have the possibility of having some internal dynamics in the dark sector, meaning that the relic density is not only fixed by the interaction with the standard model, but it could also be fixed by the interaction within the dark sector itself. And that gave like amazing names like cannibal dark matter, or pandemic dark matter, selfish dark matter, whimsilla, simp, co-annihilation. I mean, okay. You basically find a name, and this theorists have an endless imagination for names, I think, especially in this particular regime. So each of these names basically tells you like a different mechanism to get the proper relic density out of a Feebly interacting particle and the light dark matter candidates. And in some cases, you have also self-interaction within the dark sector. So the model I want to first present you is a very versatile one that I like quite a lot because you can basically use it for testing a pretty big range of models in light dark matter. So the one that is called the inelastic dark matter scenario. So the idea is that first of all, you'll use one of the simplest mediator Feebly interacting particle that we have, the dark photon. So we've seen this one before, so you recognize the portal here. This B mu nu is a vector portal, and F mu nu is the dark photon gauge field strength. Epsilon is this kinetic mixing term. So if you remember, this could come from a loop of heavy particles. Now, if I want to make this model complete, I actually need to add a dark Higgs mechanism, because now this particle arises from an abelian gauge group, like a new dark U1 if you want. So I need to break this gauge group in order to give a mass to my dark photon. So therefore, I need a new Higgs particle. So if you put this together, this is the term that we have for the Higgs. This dark Higgs potential will trigger a spontaneous symmetric breaking. It will give a mass to my dark Higgs and to my dark photon. Okay, so this is a typical scenario for a massive dark photon at that stage. So the second thing we need is the dark matter itself. Oops, sorry. So for the dark matter, we'll stick to this Dirac fermion idea that we had before. But if you remember, we could not use a Dirac fermion per se, right? Because as we've seen, it's an S-wave annihilation. And so it would proceed without any suppression in terms of the velocity. And because this dark matter is light, it will give you troubles with the CMB. Because the simplest way of avoiding this problem is, in fact, starting from a Dirac fermion dark matter, but not realizing that, wait, you have a dark Higgs, so you can write Yukawa couplings. So these two Yukawa couplings here, they're a bit peculiar because, as you'll notice, they have this kind of Majorana mass term here. So instead of being like the standard one where you have Dirac constructions like left, right, this is two Majorana constructions, and you can do it because the dark Higgs can have a charge +2, for instance, and the chi -1. What is very interesting is once you do that, the Higgs wave will split your Dirac fermion. So you see that the mass matrix for my states is now m chi. And now because of this YSL and YSR, I have also Majorana mass term in the middle. It means that you need to diagonalize this mass matrix, and instead of having one Dirac fermion dark matter, I have now two Majorana fermion objects. The lightest states will become dark matter, and the heaviest states will become some excited new state. So you see that the spectrum looks something like that eventually. You have the mass of your V, the mass of your dark Higgs, and then you have two states. And the nice bit is that you can completely control the splitting between those objects as a function of the wave of the Higgs and the Yukawa couplings. So you can very easily put yourself in a situation where you have two states with a very narrow mass splitting. This is very important because the annihilation in that regime will be given by what is called the co-annihilation setup. So this is the one I showed you here. The idea is that once you calculate the annihilation of this kind of particles, the dominance occurs from having chi1 into chi2, V E plus E minus. Now this escape very neatly CMB bounds for a simple reason. This chi2 is an unstable state. It will want to decay back into dark matter. So at late time, by the time of the CMB, for instance, all of the chi2 will have disappeared from the thermal bath because they have long decay into chi1. So once all the chi2 have decayed, that's the standard co-annihilation scenario, you just don't have any possibility anymore to annihilate dark matter. And so therefore, you have no indirect constraints and no CMB limits. So that's a neat way of avoiding what I showed you, the CMB constraints. The second regime that comes out quite naturally is what happens when the dark matter mass becomes lighter, but just a bit, than the dark photon. So these types of annihilation are often called secluded, because basically you see that here, the entire dark matter relic density is fixed by dynamics within the dark sector. So now it does not really depend anymore about the coupling with the dark photon and the standard model. It just comes from the fact that, well, you have a certain coupling between dark matter and dark photon, and later the dark photon will just decay out into standard model particle. So this is like another regime. And to that, I can also add another regime yet, which happens with the dark Higgs. So putting all of that together, you see that as function of this mass of this dark Higgs and the mass of my mediator, you have kind of a whole phase space of different mechanisms to get the relic density. So this is very interesting because it means that you can study all these different regimes from the Finot perspective. And in particular, the regime in which you have the inelastic dark matter, so this one here, is very interesting from the experimental perspective. So this makes a bit of the link with what we did in the first lecture. So you should recognize some of the experimental name that we had. So for instance, you have Babar here, an E plus E minus collider, which looks at missing energy. And then you have plenty of other limits. So this black line here, the thermal target, so you see that we've covered already quite a lot. All those experiments here, CHARM, you should remember this one. This is the beam dump facility that we had. So it looks at a long-lived particle. So here, typically, we look for the decay of the chi2. And then you have all this sequest, GSN, Icarus. Those are neutrino experiments. So this is a very broad scenario in which basically using your IDM, you have very good prospects to study that in the collider world. Okay, so before we go to the actual direct detection part, I will just go to introduce another model. Basically one model in which you'll try to bypass this cosmological wall that we see. So we'll try to get a dark matter mass lighter than the MeV. So to do that, basically we have to do two things, take care of the neutrino decouplings and make sure that we don't mess up with BBN too much. So typically here you have what happens when the decoupling of dark matter occurs from freeze out as function of N effective. So what happens here is that you see that basically once you're out of something like 8 or 5 MeV, depending on the model that you are in, you're shifting the number of effective degrees of freedom. This occurs because dark matter annihilation will inject entropy into the thermal bath of the standard model. And if that occurs after the neutrino have decoupled, it will change the effective number of neutrinos. So basically, this is a measurement of how much entropy you're putting into the thermal bath of the standard model with respect to how much is into the neutrino bath, which has no decoupled. So, I mean, from the pheno perspective, this N effective just comes from Planck measurement, and so it's a constraint. And basically, you see that if you have something which is electrophilic, you can hardly have a Dirac fermion, for instance, below, let's say, 8 MeV or something. And of course, it's a bit better if you have some scalars around. So how can we bypass that? The first bypass, which is a bit hard, is to assume that you will have some interaction with neutrinos, so that when the dark matter annihilates, it will inject entropy both into the standard model bath and into the neutrino bath at the same time, so that it would compensate out. What is a bit more interesting and that I'll discuss now is the possibility of using another mechanism to fix the relic density called freezing. So freezing is something that has been known for a long time, which typically occurs as soon as the couplings are extremely tiny. This is a very well-known diagram there. Basically, in freeze-out, when you decrease this coupling, you tend to increase the relic density of dark matter. This is because it gets harder and harder to annihilate dark matter, and so therefore you are left with too much dark matter at the end of the day. Freezing is the opposite. You suppose that you don't have dark matter from the start, and that you're producing it little by little. And so if we increase the coupling, you produce more dark matter. What is very interesting is that, I'll come back to that in a second, and in some of the models, but you see that in freezing, the production stops at the mass of the dark matter. Meanwhile, if you are with freeze out, the annihilation stops at something like 1/13 of the mass of the dark matter. So that means that it's significantly easier to escape this kind of limits if you're from freezing, because basically you really decouple your object at just one mass in particular, not at the mass divided by 30. So, okay, let's come back to that a bit. But before, I just want to point out what is freezing. So I took this from Francesco De Ramo because I really like the picture. The idea of freezing is that you start from something that is the full thermal bath particle. So all these B here are bath, so thermal bath particle from the standard model. And little by little, you just add a bit of dark matter. And there is just not much of it, at least not enough that this dark matter might annihilate. But you're still adding a bit more and a bit more. So to do that, typically requires a tiny interaction with the standard model. Now, Feebly interacting particles are perfect for that because we have a lot of tiny interactions around there. So if we take, for instance, what we looked at the last lecture, the Higgs portal, this is a typical potential that we had, if you remember. So you have the interaction between the dark Higgses and the Higgs doublets itself with A lambda HS. So if you just take this model and now assumes that, well, these couplings are tiny, what do you get? Well, you can assume that this new dark Higgs is now interacting with some dark matter particle with a tiny coupling Y, and that it interacts with the standard bath via this lambda HS here, which can be quite big a priori. So now you're in a situation where the dark Higgs is in equilibrium with the thermal bath, but it will decay very rarely into dark matter. And this you can just arrange by having a tiny coupling. So you take Y chi 10 to the minus 12, for instance, and the dark Higgs will decay very rarely into these objects. So what you get then is that as the temperature of your bath goes toward the mass of my mediator, which is the dark Higgs here, you see that the particle tends to like increase, and then you freeze in. So the reason is quite simple. Once you reach the mass of MS, MS will decouple from the thermal bath, and so therefore it will not be recreated. And so in a way, once you've actually produced, so in a way, once MS is decoupled, so once the dark is decoupled, you stop producing dark matter altogether. And so then you're stuck with the density of dark matter that you had from before. Okay, so that's typically what you have here, this different freezing line. And so you see that what is funny, that basically almost all of the production of dark matter occurs around the time where the temperature of the thermal bath is around S. The very simple reason for that is that this depends on the time, basically. But the temperature is when the inverse of the time in the early universe. So basically, even if this is like a small range in temperature, this is where you have the most time to produce the particle in the first place. So this is why you have this kind of thing. And what is very interesting, as I point to you again, is that this occurs for masses of the order of the dark matter mass. So this is a model with dark Higgs. You could do exactly the same with the IDM model I showed you before. The only tools to do that is to take the dark photon extremely light, so with a mass below the EV, the MEV, and make a tiny kinetic mixing to make sure that you don't hit too much of the limits I showed you before. So, 10 to the minus 10. And then that gives you this kind of models here. And there's a model put by Dvorkin et al., which has the advantages of being super simple. So they looked at this kind of processes, which is more or less exactly the one that we've looked for, except that when MV, which is this gamma prime, is tiny and the kinetic mixing is extremely small, then basically you start doing freezing instead of freeze out from those objects. So what they looked for was the limits from all these cosmological constraints I showed you before. And you see that because the freezing occurs at temperature which are much closer to the dark matter mass, not the dark matter mass of the 30, the limits are much better. So typically the limits on effective for Planck's goes all the way down to the keV, the 20 keV regime. And then we have also very good prospect, like the Rubin Observatory for small scale constraints could push it even better if it's really like not showing any particular signature. So this is quite interesting because in one way, the model is a bit, it's not as elegant as freeze out because you have to assume that the dark matter is not produced from the start. On the other hand, it allows you to make very strong prediction on the cosmology and the astrophysics. It's not often that your actually dark matter model could be like ruled out by purely astrophysics. So this is quite interesting. The second thing which is interesting is that it has a very peculiar direct detection constraints. So if you look at the model of sub-GeV dark matter I showed you before, this inelastic dark matter, then in certain cases you're very sensitive. So this is from the slightly older results. So I don't think there is Edelweiss on that, sorry, Corinne. But the idea here is that all of these lines there are different model of sub-GeV dark matter. So typically you should look at this orange line here is more or less the inelastic dark matter model. So basically you see that it's almost impossible to reach to this place. And the reason is that the scattering velocities as suppress, the scattering velocity will be, the scattering cross-section will be suppressed by the velocity of the halo particle in these models. Or if you're in a co-annihilation setup, the only scattering you could do is an up scattering toward chi2. So you'll need a lot of energy to be able to go to chi1 and move up to chi2 in your scattering. So that makes it very hard for this kind of model to be actually probed by direct detection experiments if you don't have some subfraction of relativistic dark matter, for instance, in your halo. On the other hand, if you look at this very light mediator aspect, so there's a freezing model I showed you before, you could go to very light masses. So there's this freezing model here. And because the mediator is very light, you have a huge gain into the scattering cross-section, which comes from the 1/q squared here, which is exchanged in the mediator. So this allows this kind of model to have a very nice signal. And this is one of the models that they could probe in direct detection experiments focused mostly on light dark matter objects. Okay, so I think, yes. So I think that concludes part of this discussion about first dark matter. So I would push to get a bit of a break now. So maybe first, do you have any question on that? Yes, no?
I can start.
Yes.
So here you're giving a mass to the dark photon by using a scalar that you...
Yes, let me go back to the IBM model, yes.
A nice feature from that is that then you can write some Yukawa-like coupling, giving you Majorana mass-like mass terms.
Yes.
And you can play with those coupling to achieve in the right parameter space.
Yes.
And what I was wondering is that at the end, I mean, when you started, what is inside the rectangular is that I mean, a vector field that mixed with the photon. And that, for example, in the standard model, we have the raw meson that mixed with the photon.
Yes.
And is there dark matter model in which the dark photon is a resonances from another sector? On
So, okay. So typically this raw resonance, for instance, is something you can see it here. So do you see this kind of feature here? It occurs because, so here you see that the dark photon is 3 times heavier than the mass of the dark matter. So that pushes to the row. So what happens here is that basically the kinetic mixing triggers mixing between the photon and, no, I mean, it's not really a mixing in terms of mass mixing, right? If you remember, this is more about mixing self-energy that you need to renormalize properly. What it gives you, it makes this object eventually takes a bit of the contribution from the electromagnetic current. But because of that, of course, just like in vector meson dominance aspect, in which you just said that, oh, I'm going to mix my photon with the rho, the omega, and all of these vector mesons, you can do exactly the same thing for the dark photon. Now, on the question whether or not this could be done like as a composite state for another sector, I think the answer is yes, to the best of my knowledge, although I'm not sure of a model in which that was actually a good question. I cannot find back like a model in which that was done explicitly. But yes, I mean, there is no reason for that not to occur. I mean, for instance, let's take a simple construction that you, in your dark sector, you have, let's say, technique works that are going to confine to create you a row. But then some of the from some of the anomaly cancellation tells you that at the TV, you need new vector-like objects, which couples both with the technicolor and with color. And then they will mediate a loop of those objects. And so eventually in the low energy theory, you'll find out that. Now, does it actually change something for the V? I don't know. I mean, at least from the standard perspective, I don't think that will make any change. Except that you may have a V with a very large width. So that's maybe an issue. But the truth is that you already have a V with pretty large width here, because typically I take couplings there with the interaction between the dark matter and the V is supposed to be of the order of 1 or something. So that means that this V has typically a pretty large width usually. Because if you take it smaller than 1, then if you remember this, these things. If alpha dark is tiny, then it means that epsilon has to get bigger. And so therefore you start to get excluded by direct detection and collider searches.
Okay.
So, but yeah, I mean, I think in principle, nothing prevents you to having that. I mean, it's like that then it would be just a standard approach. No, I mean, will it actually make differences? This is another question that I don't know.
Yeah, that what I was wondering is then after when you write your Yukawa like couplings, maybe you get more constraint in this kind of composite models.
Yeah, that may well be. I mean, it's entirely possible that we may construct a model in which you have fully composite dark sectors, in which the breaking does not occur from a Higgs sector, but from a confinement scale. And then dark matter becomes the pions in the sector, for instance.
Yeah, they would be like pions, yeah.
So yes, I think that's fully viable. Then the only question again is that you need to make sure that if it's you need to make sure that the annihilation cross section is suppressed in terms of V, because I cannot know for sure before actually calculating stuff.
Okay.
But this I don't know. I mean, in particular, yes, I think you can always try to match these things to different objects in the dark sector. Like, I don't know, pi plus pi minus there. So yes, I mean, in principle, I think this could be interesting to construct, yes. I don't see an obvious reason why this would be impossible.
Okay. But you don't know if this has already been done or...
I'm not aware of that, no. I'm aware of some models in which they had some confinement in the dark sectors, but you probably know this better than me. Like models that like dark matter and stuff like that. I'm never aware of something in which you had a light dark matter. One difficulty, I guess, is that the confinement scale would have to be quite small.
Yeah, exactly. Usually it's
And
quite
how
heavy.
do you
So
hide the objects? But maybe, I mean, it's not impossible, right? You can perfectly assume that the actual particles which would be charged on both the standard model and this dark SU3, for instance, would be at the TV, so out of reach.
yeah, making
And then
the
you would have some very light particles which are just SU3 dark charged. And then you would build from it, let's say, two sets of SU dark quarks, for instance, like Q and D. And if they're not yeah, and in principle, yes. I mean, if they're not interacting with the standard model in any other way than the TV particle, then a priori, I don't think that will change anything.
it will be interesting. Okay.
Yeah.
I will look a bit in that.
Okay.
Any other
Another
questions?
question then before we have the break, and then we'll move to the rest of the final.
Yes, Luc, thanks for
You're
this
very welcome.
lecture. Just about your last slide, and this is from my
This one.
experimental point of view. What do you think about the best way for an experimenter to cover the model you propose? Lowering the threshold, of course.
Sorry, Corinne, I really don't hear you very well.
Oh, sorry.
Just because I'm at home.
Sorry. Can you hear me?
Yes, it's much better now.
Yes. Sorry. So I say thank you for the lecture, and my question is, do we need to lower and lower the threshold in direct detection experiments to cover the model they propose? We can compare, for example, for Edelweiss, we can compare
yes, exactly.
with super CDMS, of course.
Well, cryocell should be able to do much lower, right? If I remember properly.
Yeah.
In MK. Now, the thing is that there's also why I wanted to do it, because you see part of the in really sub-GeV dark matter models, the truth is that most of the, I mean, there will be some models testable, but those are very strange. Like this elastic scalar, for instance, is a bit of a, I mean, it may work, right? But it has been already probed by Sensei, more or less. And then the models which are a bit more complex, let's say, like these IDM models, are pretty much out of reach because of the upscattering that you need. So the only possibility is either to have like another flux of dark matter, which is relativistic and not so produced by cosmic rays, for instance. So this is why it was interesting for me to look for this lighter mediator approach. So basically try to get something below the MeV with a very light mediator, because this has a 1/q square, meaning that each time you lower the threshold, you gain a lot in cross-section. So, I mean, if you see the propagator for this A, write it a second there. Yes, it works. So basically it's, you could not see the bottom of my screen, in fact, before. Okay. So if you actually look at something like that, for instance, so chi, and then you take V, the V that we showed before, this is proportional to basically the 1/, so then you have an exchange momentum here, which is q squared. So it's proportional to q squared minus mv squared. Yeah. And the truth is, like, if mv is at the MEV scale, like in this IDM model, you don't gain much. But if you look at these freezing models, what is super nice is that because MV is very, very small, in principle, you can increase the scattering cross-section dramatically by going to small q square, meaning very small recoil.
So, sorry, Luc, what is the typical scale for MV?
So this is a choice. In these models that I showed you in IDM, MV is above the MEV scale, meaning that this q square is very big. If you are in this model for freezing, MV can be almost massless. I mean, it could be the electron volt or whatever. In practice, you just assume it to be tiny, extremely small. And because of that, it means that in principle, you're not limited by this mv square. It behaves almost like a photon. It's just the same as mealy charged dark matter, for instance. And so therefore, you just want to get to as small a q square as you can. And then, of course, having lower threshold helps a lot.
Thank you. Thank you. We'll try to do that.
Yeah, I mean, we can discuss it later again on this part. But I think that's part of the truth that this kind of model that I did not study them too much before, but they're kind of interesting because you lose a bit on the theory side, on the attractiveness, because, okay, it has some parameters that are a bit strange. You use freeze-in, which is a bit less attractive as a dark matter mechanism as freeze-out. But then you gain quite a lot because you gain like the possibility of looking for these guys in astrophysics and the possibility of looking at direct detection experiments to look for that. So these two things together makes it quite interesting, I think.
Sure, you're right. Thank you.
Okay, so I suggest we take at least a 5-minute break, at least for me to get a coffee. And then we can come back. So at 15?
Perfect.
Okay,
Perfect.
see you very soon.
See you soon.
Okay, so I have a full signatures. Okay, so in this last part, I will try to explore quite briefly, I would say, some of the different pheno aspects from low energy observables that we'll have in the presence of feebly interacting particles. So, okay. The first thing I'd like to come back to, which should not take very long, but it's a pretty important topic nonetheless, is the question of how the presence of a feebly interacting particle can lead to flavorful signatures. So if you just want to like make a very brief summary of where we are in the standard model and this issue of flavor, here it is. So basically, I remind you that the standard model comes in 3 generations, of course. Now, from the gauge perspective, they're all absolutely and completely equal. And it's only the Yukawa coupling which actually provides a difference, meaning the interaction between the Higgs boson and each generation is not the same. So that implies that it generates a huge discrepancy in masses, which is the generic flavor problem of the standard model. And on top of that, it also allows for flavor-violating decay to proceed because of the rotation of the weak current in the CKM matrix. So if we want to make that a bit more quantitative before moving on, this is a standard Lagrangian, right? So the Yukawa coupling are by default 3x3 matrices. Now, what's pretty important is to realize that we don't really know those objects. At least we don't know them very well. We know some of the interaction, for instance, between the Higgs and muons, the Higgs and B, because we've been able to measure it. But the off-diagonal components, the left, the right, all of that, we don't know much about it. So this is the goal of the flavor completion of the standard model to explain the structure of these Yukawa matrices. Okay, so of course we have, so here typically I took down and up quark. So what is of course interesting is, as you know it, is that once you break the SU2 cross U1 symmetry from the Higgs wave, this will transmit the potential flavor violation, which is in the Yukawa couplings, to the weak interaction. This is because basically the weak interaction couples together up and down quark, which have different Yukawa objects. And so you construct this matrix that you know is the CKM as the rotation for the up and the rotation from the down. It just turns out, and this is kind of not a surprise, but it's a result per se, there is no reason for it to be in this way, that this matrix is almost diagonal with some tiny off-diagonal contribution. So in the standard model, this is how you can pass from one generation to the other. So typically, this is the kind of transition that we'll be interested in. So you start by some objects, for say the B quark, and then you want to decay it into, let's say, a D0. And so you want to do that how? You want to do that by emitting a weak current, which will be able to take a B, which is a 3rd generation, into a 2nd generation. So of course, it also means that in the standard model, these kind of processes are extremely suppressed, right? They are suppressed because one, the W mass is quite big, and second, it has a factor of CKM suppression, which if you remember from this parameterization here, is quite large between between the first and second, 0.2, but even smaller between second and third, which comes to the square. So this gives you a quite strong suppression, and that means very long lifetime. So this is part of the interesting bits. So you see that here, what I'm showing you are mesons, so composite objects made from heavy quarks and light quarks. So the fact that they are confined one to the other is due to QCD, but the decay here is due only to the weak interaction there. And because this weak interaction is very suppressed, it typically means that you'll come into very long lifetime when you deal with the decay of this kind of object. Because the only way you can go from a third to a second generation is by emitting something like a W, or some loop factors. This means that you have an enhancement of the branching ratios for a very simple reason. If you want to look at something that is very rare, it means that you have a tiny decay width, this gamma here, but if the lifetime is very long, then you gain a lot. So basically, it's significantly simpler to look for a very rare decay when your particle is very long-lived, simply because you don't have a very strong enhancement. It does not have like a simple way of decaying already. So the branching ratios are automatically smaller, even if the width is quite tiny. Additionally, because if the lifetime is sufficiently long, you can actually try experimentally to produce pure mesons beam. This is what we do with kaons, for instance, k long. If the lifetime is long enough, you can produce the particle and then propagate them. And in this way, you're absolutely sure that you can end up with a beam which has a good amount of purity in terms of the particles that are in, meaning that it's simpler to look for decay rates. So what is very interesting that these flavors of transition provide an extremely powerful constraints on Feebly interacting particle. So this is kind of a small summary of what you could do, for instance, with some of these rare decays. So this B2K, not B2D that I've written here. But you see that from this kind of decays, you can constrain interactions. So here I'm taking an axion out portal. So if you remember, this is constructed from a fermion portal, which is two fermions of the standard model built together with some new physics objects which couples derivatively. So that's dimension 5. So it goes as 1 over FA. It means that it's generated by some UV physics at the scale FA. So what we see now is that if these UV physics predict an order 1 breaking, so an order 1 coupling between second and first generation, S and D, for instance, then these couplings is extremely constrained, and we're pushing something at 10 to the 11 GeV. So this is remarkable in a sense that flavor physics is allowing you to test, let's say, the generation of couplings up to extremely large scales in principle. This is something that we've known already from a standard, let's say, SMEFT approach, for instance, or effective theory approach of this kind of decays. The main change here is that because these particles are light, they can be a priori produced directly from the decay of the mesons. So you don't need enough shell particle like a W here. You are able to produce it directly from the decay. And so you move also from a 3-body to a 2-body decay, and so it's even more constrained. Okay, so how can we do that from the practical perspective, right? So from the practical perspective, I will hand you over a current written in terms of quarks, for instance, in the standard model. So there's typically a fermionic portal with quarks. Then you'll have to move it toward the couplings below the electroweak scale, so typically written in terms of Dirac fermions. And because we're interested in an object which are confined into mesons, you'll have to apply different techniques to actually calculate the decay rates. So, I mean, moving from the hardest in KPT to some easy one in VMD, and the simplest one from factorization. So in fact, we'll do a calculation now based on this factorization just to try to get a bit of a handle on how the constraints can be used and how we can actually measure this kind of objects. Okay, so yeah, let me move to that. This is the last time I promised that we actually move toward writing something here. So the goal that I want to have there is to just give you a bit of a taste of how you can use this mesons decay to actually constrain and predict what will be the production rates of Feebly interacting particles. So for that, we'll base ourselves on one of the simplest cases that we can do, which is the heavy neutral leptons. So if you remember, heavy neutral leptons are sterile neutrinos, right, in a sense. And so they are defined by the fact that they have a mass and a mixing with a neutrino. So typically they're defined by the mass Mn and a mixing angle theta, so that you can have something like neutrino theta going into N. Okay, so what we're trying to do now is to calculate the prediction rates of those objects, actually one of the dominant prediction rates for these types of heavy neutral leptons, and also one of the constraints, actually. And this process we'll be interested in will be Kepler's into dileptons. So basically, we want to study the purely leptonic decay of a kaon, a charge kaon. So in the quark model, how does it behave? Well, we're in a situation when we are a kaon, then we have a U, then we have an S bar, and then these two objects are ups. And from the Feynman perspective, you'll want to write something like this, right? It's a W, and then this W will interact with an L and a nu, and potentially a right-handed neutrino. So if I was just interested into this part of the diagram, this one, this is simple, right? This is just about having some quarks interaction. So at LHC, that would be very simple to calculate that. This part here, meaning like how does this quarks interact and form a kaon, is where, of course, confinement occurs. So I cannot know that really from first principle. What I need to know and what I will use in the following is that this is a very simple process per se. I'm starting with an object which is on its mass shell at rest, and I just want to decay it into a pair of objects. Additionally, I know that whatever QCD is doing, it will have nothing to do in this vertex here, which is purely a weak interaction. So therefore, the first thing I will be interested in is that I'm expecting that the full amplitude will be proportional to something like that. Oops. I will make this insertion of vacuum, and in the meantime, I will put the currents here, the quark currents, and there basically what I want is as final state my leptons. And here, of course, you want to put just the leptonic currents, so an L, and the same thing, gamma mu, gamma 5, nu. So the factorization hypothesis is that normally my amplitude should be given by this thing contracted with this one, with in the middle 4 fermions operator. Factorization implies that whatever QCD is doing, it will not have much impact on this part, which is purely weak interaction. So it's easy that it's enough that I calculate first this part of the amplitude, and then I'll just match it with whatever the weak interaction is doing there. So it's of course extremely effective, at least for this type of processes where basically you just look at the decay of the particle and it entirely goes with it all. And it works as long as you have purely local effects so that you forget about charm loop or this kind of thing. So let's start with it from now. The first thing is that this part here we can know because, well, it has a very simple shape per se. In fact, this is exactly the definition of the decay constant of what is the kaon itself. So we have only one momentum in our problem, which is the impulsion of the kaon. So let me write it here. So here, oops, the kaon has a p. So this is the only vector that I can write, and because this is a vector, I can construct it this way. So this is what is called the decay constant, and typically all the decay constants are kind of the size of the QCD scale. So this is 100 of MeV. As a matter of fact, this is something like 150 MeV, if I remember properly. But we will not need it, because all the gain here will be to try to make the calculation, and then compare what we will predict for the right-handed neutrinos to what we have in the standard model, so that we can just measure the standard model and predict what we'll get for the right-handed neutrinos. So now that we've done this part, which was the hardest, we just have to plug together this currents here. Zoop. So I think I'll save you for the full calculation here. Basically, what we have is what? We'll need an interaction from 2 weaks coupling, because we have W interaction. We need the VUS. Why? Because if you actually come back to this diagram here, this is G, but here, G2 over square root of 2 actually. But here you see that this has some flavor violation built in. So I need the CKM matrix, that thing. So you see that the CKM matrix enters these expressions, and then basically you can try to calculate the rest of the impulsion. That's very easy actually, because only the longitudinal modes of the W will contribute there. which means that if you actually make the full calculation, which I will not force you to do, you get something like that. So this is P mu, then actually the entire, okay, I will do at least part of it. So this is a propagator, P mu divided by mw squared. So I go into the unitary gauge for the propagator of the W. Then what is P square? Well, this is the decay of a kaon, right? So P square is exactly equal to the mass of the kaon. Because if you look there, this is the decay at rest. So you can hardly make a more simple process to look for. So that means that you have P mu, then you have mk square minus mw square. Okay, very good. And then we just have to get the leptonic currents, which are something like gamma mu, PLV. And there is a PL because, well, it's a W, so it interacts only with left-handed currents. Okay, so this part is very easy because you see that now my P mu can contract here and it can contract there, but when it contracts here, it will create for me another m kaon square, so that eventually this whole thing will simplify to 1 over mw square. There's just one trick that I want to show you for this, that at that stage, the P mu will just be directly contracted with the gamma nu here. So at that stage, you can, of course, turn to one fine calc to calculate the entire diagram. There is something a bit interesting occurring here, is that if you remember that your leptons are on shell, you can dramatically simplify the calculation even before just going through. And this can be done quite easily because you see that once my P mu goes and get contracted with the gamma mu, I have something like that, P slash PLV. But now P is also equal to K1 plus K2. So the final state here of impulsion K1 and K2. So what this means is that this is K slash plus K2. But my leptons are on shell, which means that they have to satisfy the Dirac equation for fermions. And one of them is basically massless. Those are the neutrinos. So in fact, you can just contract those. The U is for the, which one? Okay. So the U is K1, which is the neutrinos, and this is K2, which is the leptons. So altogether, it means that this will proceed. And once I apply the Dirac equation on those objects, instead of giving my K slash, I will just directly extract an ML. So this is very interesting because you learn something from that even before actually making the complete calculation. Oops, eventually you end up with something like that. You see that now my decay rates are proportional to the mass of the leptons. There's something which is logical because of the fact that the only way you can decay the kaon is a pseudoscalar particle, right? Yet I'm writing a propagator there with the W's. W's are vector particle. So it does not make a lot of sense per se that you said, oh, I'm having a particle which is a scalar, which would oscillate at the quantum level into a W. An offshell one, right? But still a W. So the only way for this to work is if you don't go into the transverse mode of the W, but the longitudinal modes. So basically what is important here is that it's not the W, it's the Goldstone modes from the Higgs, which makes the exchange. And the Goldstone modes have couplings proportional to the mass of the leptons. So therefore, eventually, you generate mass of the leptons here, which will suppress it even more, meaning that the kaon will prefer going into muons way more than into electrons. It also means that if I decay into, let's say, something that is not a neutrino, but rather a right-handed neutrino with a significantly larger mass, this should be also included and it will lead to a larger decay. Okay, eventually, I mean, you can make the full calculation from that. So that's a decay. So you have 1 over 16 pi. Then you have square root of final state. Then you have the mass of the kaon to the 3. And then, as usual, you have to take the square of the amplitudes. Okay, I'll save you the rest of those calculations, but if you just proceed all the way to the end, you get something like this, meaning that you have the mass of the K divided by 8. Then you have the weak coupling to the 4th. Then you have the CKM matrices. So remember, we knew that this had to be there. Then you have the 32 pi. Then we get this dependence on the lepton masses that are advertised to you that will tend to suppress those couplings. And okay, if you do everything properly, you have some kind of form here that goes there. Okay. So what is very interesting now is that this is the process to earn mu. But remember, my right-hand neutrino is basically the same as a neutrino. You just have some mixing term. So from there, you deduce right of the box that if you have, let's say, the mass of n much smaller than the mass of the lepton, for instance, the muon, and the mass of the kaon, then basically everything behaves as if this guy is the same as the neutrino. So the only thing is that Ln will now have some tiny suppression in theta times gamma to L nu. So actually, if you make the full calculation, you'll find some additional discrepancy from there. I mean, especially if the mass of the right-hand neutrinos is non-zero, then you'll find some kind of new kinetic factor that you can very easily find from the full cross-section. But what is interesting is that from this perspective, you see that the branching ratio of K plus into neutrino L plus is basically, right-hand neutrino is basically the same as just the sinus of this mixing angle square times the branching ratio. Oops, okay. So what this tells you is that even if, let's say, your particle, here the right-hand neutrino, does not have per se a flavor violation, like the ALP, it's still very important to look at flavor violating decays. Because, well, this is the best way of looking at processes. And this is, in fact, it turns out that there's a dominant production mode. Production mode for heavy neutral leptons around the kaon mass, typically. And you can also use that to put some constraints, because if you're able to measure the K plus to nu L plus, then you can use the right-handed neutrinos to constrain the full limits. Okay, so this stops a bit. So that was just a small bit on actually how we can do and how can you treat, let's say, the decay of light mesons when you have access to a Feebly interacting particle. So as you can see, mesons are absolutely critical in the decay of, in the production of Feebly interacting particles because, well, they're both light and often they have a pretty long lifetime, meaning that it's the best place to search for rare decays. So I think I'll just finish this whole lecture and also part of this pheno on the discussion between Feebly interacting particle and the anomalous magnetic moments of both the g-2 muon and the g-2 electrons. So, okay, this is a bit of another bit, but it's one which is very interesting. So we are in a bit of a strange situation for those kind of objects. On the experimental side, we had a very good confirmation that the decade-old anomaly that was measured first by BNL was really still here compared to the estimate in the starter model. So we had an anomaly at almost 4 sigma. Now, this is something that a priori is extremely interesting for light particle. The reason is quite simple. The g-2 is an observable which feels physics at typically the mass of the muon. Because, well, this is the typical mass that flows in this loop here. So when you have a particle which is very light, in fact, you need a very strong suppression of its interaction to make sure that you don't overshoot on the g-2 of the muons. In fact, I mean, we used to have, let's say, in a TV scale, new physics objects, which requires very large coupling so that you can actually make a dramatic shift to the g-2 of the muons. When you're in the situation of having Feebly interacting particles, it's completely different. You need a pretty tiny coupling. So for instance, if you have an object at the MeV, so at the GeV scale, you need couplings at the percent level also. What is very funny is that this has been something known, but for ages, literally. So, I mean, I went down and trying to actually find the first time people looked at the g-2 and tried to put constraint on line new physics. I was able to go all the way to Brodsky in 1967. And I'm pretty sure that there are other discussion on that even before, because basically the g-2 was one of the first observable that we had. We could validate QED, and people very quickly realized that it could also be used to test for the presence of new objects, which would interact like a photon, but a bit more heavy. So what has been a very important experimental advance of recent years, let's say, is that the prediction that the d-2 anomaly would come from a dark photon, so if you remember one of the simplest FIP scenario that we have at hand, has been excluded. And this was one of the biggest results, in my opinion, from Babar in this kind of physics, that it basically covered it almost entirely. And on top of it, yes, and an A64 basically finished covering the whole thing there. So that tells you that the light mass regime is excluded for the vanilla scenario of dark matter. So if this is a real anomaly, it cannot go with just the dark photon. So the thing is that even though we can just look at the g-2 muons, in truth, we are at a bit more of a troubled time that this picture before it would show. We're in a situation where, on the good side, the experimental average is very far away from the data-driven approach. On the bad side, we had lattice QCD results, which would tend to show that the actual standard model prediction is significantly bigger than what was assumed. So that includes this BMW, but in fact, in the 2 last months, we had 2 other papers from QCD and one from today, I think, which were going into the same direction, claiming that in the lattice perspective, this is a bit bigger. So that, of course, raises quite a lot of questions because the data-driven approach is quite solid also. And so one should wonder why you would have such a discrepancy, basically, between both the lattice, the data-driven approach, and the experimental average. If you look at the g-2 of the electron, the situation is even worse, in fact. So we are in a situation where we have 2 experiments, one at LKB and the other at Berkeley, which measured more or less the same thing, and which predicted exactly opposite values of the delta A, so of the g-2 of the electrons. So typically you see that you have something at the 10 to the minus 13, which is very interesting, because this is basically where you would expect the g-2 electrons to be with naive scaling if the anomaly here is true. But you see that it's a bit of difficulty, right? Berkeley was pushing to a negative value at almost 2 sigma, while the new result pushed for a positive value at 1.5 sigma-ish. So of course, this makes us a quite different situation because a different sign means completely different physics between both. So it's pretty clear that on the pheno side, we really don't have a very nice target to fit anymore on this kind of approach. What is nice for Feebly Interacting Particles is that they don't really care in the sense that they can fit pretty much any value you actually send. So whatever will be the actual value will just be some improvement or modification of what is the actual range. So if there are anomalies which are confirmed in both g-2 muon and electrons, for instance, then Feebly Interacting Particle will be quite nice and then they're versatile. So one of the model that I'd like to show you for this one is the Naxion-like particle. So it's another good example to show you the currents again. So you should recognize particle operators by no quite easily. So Sharam, you can see that here, for instance, you have an F mu nu tilde. So this is the ALP portal. And this is another fermionic portal, again with an interaction with an ALP. So the idea is that ALPs, or Naxion-like particles, that I did not discuss too much before, are very interesting for the g-2 because they have a very large freedom in the way that you can get the g-2. Because first of all, you can use this kind of diagrams here, where you have the muon or the electrons, and then you exchange a loop of an ALP, and you emit a photon. That's a vanilla case. This predicts to you a negative contribution. But because an ALP has natively an interaction with photon, you have also this kind of bar Z diagrams, where you can have both the photon and then the ALPs which interact with the lepton and with the photons. Now, what is very interesting is that this diagram, you see, it does not have the same coupling square, like is typically the case in most physics model. It has one coupling here of leptons, another one on photons. So by changing the sign, you can change this full sign of your contributions. So, okay. So what are the constraints that we can look for that? I just want to make a small aside on the types of constraints which are relevant here. So in most of the talk before, I showed you constraint on visible decay. In principle, if you look for Feebly Interacting Particle, there is a second very broad range of constraints which are called missing energy searches. Mixed energy searches is the exact opposite of looking for a beam, for a bump into a distribution of invariant mass. The idea is that, on the contrary here, you want to make sure that you have some missing energy in your events. So one of the simplest, one of the strongest constraints and one of the simplest experimental strategy is to look for missing mass in processes like that. So this is what E plus E minus colliders do, like Leb, Bavaro, Bell2. They look for monophoton search. So you see that you have E plus E minus, you emit an object here, and the photon there is very important because given that you know the center of mass energy of this pair of electron-positron, the form momentum of the photon is actually tracking the missing mass of your particle here. So that means that you can completely reconstruct your events, and you have a very good trigger by basically looking at a single monophoton, which are highly energetic. The second class of constraints, which will be, it's a bit different from what I showed you before from SHARM or this kind of experiments. Here, the idea is that you look at a machine for which you really know the energy of your incoming particle. Then you make sure that you're shooting at the target one particle at a time, so that you really know when something enters your detector to a very good precision. So what they would look for is a production in the target where the ALP, so this kind of processes, for instance, so this is a Bremsstrahlung of the ALP of the magnetic field of the nuclei. And the ALP here will take, it's just like a Bremsstrahlung process. So the ALP will take most of the energy of the incoming particle. So what they would do, and this is a very interesting search from NA64, is that you would throw electrons, they have 100 GeV electrons. And then the idea is that you had first a calorimeter for electromagnetic and second an hadronic calorimeter. And then they would require that the full energy deposited in the electromagnetic calorimeter is something smaller than 50 GeV. Meaning that eventually, because this is an active target, you just like catch everything and say, look, just 50 GeV has disappeared from my experiment. And then the FIP would just like go on and disappear completely. And so this is a completely different business from the previous here, from the previous description there, because you have really nothing to tag in. The main signal that you expect is that you need to be really sure that the particle has entered there. And because you know your energy, you know that you cannot lose 50 GeV of energy like this. And so this allows you to search for a large amount of missing energy coming from these types of processes. So this is what we have in this plot there, where I show you Babar, which comes from this monophoton search. Delphi is the same. And NA64 comes exactly from that. So instead, it's basically more or less like what I showed you before, except that now, instead of really looking at something decaying visibly, you can look at something which decays invisibly and some missing energy. So what is quite interesting from that perspective is that because of that's the fact that the ALPs have quite a lot of way of reproducing the G-2, because they have several diagrams which contributes, you can actually engineer a case in which you have both the G-2 of the muon and the one of the electrons overlapping. And it's pretty nice because this is one of the places when we may expect to have improvement in the near future, meaning that this is one of the rare models in which we may hope, in case these two anomalies somehow survive by the time of L2, for instance, to test simultaneously to test a simultaneous explanation of both the G-2 of the electrons and the one of the muons. Okay, let me think. What time is it now? It's practically the time to finish. We have 10 minutes, so now we have a choice for you. Either you want to hear a bit more about some of the discrepancy between the lattice and the data-driven approach on the G-2. So this is something that will go about what is called the hadronic vacuum polarization. Or we can go a bit more exotic and talk about the X17 anomaly. Do you have any preference?
As you wish.
Those are fine for me, so Sharam?
For me, if you want to do both, you can do both.
Time.
Sure.
Okay.
Or yeah, if you want. Yeah,
so let's.
It's a long lecture for you too. So I mean, it's 2 hours. I mean, you must be exhausted at some point. I understand.
No, it's fine. Okay, so we'll do a bit of both then. The first thing I want to discuss is the fact that if you remember before, yes, we have a tension there that's put us a bit at the crossroad. We have a discrepancy between both the data-driven approach and the lattice. And this is just for the standard model, remember. This is about like trying to get what is the standard model G-2, muon, something that has been studied. I mean, that's a program that has started, of course, ages ago, and it's still very important here because, of course, you see that if you trust completely the lattice, the actual anomaly is much smaller, right? So there is something which makes all of these things ticks, and this problem is called the hadronic vacuum polarization. So in a way, it's very easy to calculate the standard model, as long as you have perturbative QED and electroweak objects to deal with. The main problem is this kind of diagrams. You see where you have the muons, and then here you have a loop of hadrons, for instance, 2 pions. Now the issue is that it's impossible to predict what will this be just from perturbation theory. We just don't know. And so the problem also is that you see that this at leading order is 69 10 to the minus 10. So remember, we're talking about an anomaly which is like 40 10 to the minus 10 at most. So that's a contribution at least 10 to 15 times larger than the anomaly. Okay, at 2 sigma, the 30 times larger. So clearly you must know that very well, because if not, there is no way you can actually get the anomaly from here. So the problem is the following. I made some summary plot there. Either you try to use a data-driven approach. So this data-driven approach would basically use the optical theorem and rely on measurements of, let's say, dipion production, for instance, or you use lattice. So lattice results push you there, basically, and then data-driven approach push you there. But because data-driven approach relies on many different experiments, it's a combination of all the different experimental results at once. So in particular, it's important to see that in this data set, Babar, Chloe, and B3 are actually in some 3 sigma tensions. So the more you actually look deep into this G-2 business, the more you realize that we have anomalies everywhere. We have anomalies between the standard prediction of the data-driven and the experiment, the data-driven and the lattice, and within the data-driven, we also have anomalies. So this whole thing is filled with anomalies. So one of the key ideas that I will not push too much here is that you could use this Feebly Interacting Particle to do 2 things. The first thing is to have a loop-induced contribution to the G-2. This is what I showed you before already. The second thing is that you can actually use it to change this indirect contribution. And this is something I will not draw off too much, but the main idea is that you can change the luminosity of the experiments, which have been measuring the cross-section that I used here in the data-driven approach. And the way to do that is because if you produce a Feebly Interacting particle, it can look like the Baba scattering that is used by the experimental collaboration to measure the luminosity. So, okay, this is just like to push you that this kind of Feebly Interacting particles are very important in that they can tackle both, let's say, they can tackle most of those inner anomalies in the G-2 at once. Of course, I mean, they're not the only things doing that. It's just entirely plausible that they forgot something in the hadronic spectrum or something else.
Sorry, Luc.
Yes.
I did not get completely why you can solve the vacuum polarization constraint with FIPs.
Oh, so this is a bit of a harder issue. So I will. Oops. This is actually my iChep talk. So if you want to listen to it, you will get it. The main idea is that. Let me just get you just a taste of it. This is the hadronic vacuum polarization, you see. You have off-shell photons, and this is, for instance, pi plus, pi minus. Now, this is a non-perturbative diagram, so I cannot really write it. So what I'm going to use is something that is called the Kotovsky rule. So basically, you're going to cut here and link this part to the cross-section for having gamma star to pi plus, pi minus, which you can get from E plus E minus, for instance, data. So it's not really that, but okay, you have to pick the real part, integrate, there is a kernel, and so on and so forth.
You mean you can measure from E plus and minus?
Sorry?
You mean that you can measure this?
So this typically is measured from the ratio, which is called R, which is sigma E plus E minus to pi pi.
Just to confirm that we're on the same.
Newman. So if you have these 2 things together, then it means that to get an estimate over this object, which is used to get the hadronic vacuum polarization eventually, because this is the loop that you need to estimate, then you need data, right? So you need data, but you just don't need like all of the data. You need specifically the data of E plus E minus to pi pi, the one to the rho, and so on and so forth. So the pi pi contribution dominates. The problem is that how do you estimate a cross-section? A cross-section is estimated by typically looking at the number of events divided by the luminosity of the experiment and what you think is the efficiency somehow. In most of the case that we want to measure, let's say this is easy in a sense, because we never have the precision on the cross-section there, where the fact that we don't have the full luminosity very precisely, for instance, is important. But here, remember that this is something that we need to control at the percent level at least. So we need a percent level precision. It's very hard to get a luminosity estimate at the percent level because the beam people will not tell you that, basically. So you have to estimate it yourself using, for instance, processes. So something that you know very well, and you want to measure it. So something that you know very well is the Baba scattering or the E plus E minus scattering. So typically you want to look at this kind of thing. E plus E minus to mu mu. So this you know. And so you just measure the number of events that you have and use it to get the luminosity, right? But if a FIP mimics this kind of object, process. So basically, suppose that instead of having a gamma, I have a V, here. Basically, you'll get something wrong in the luminosity. Not because you were wrong in actually measuring your number of events, but because the number of events you've been measuring has now both the standard model and a bit of new physics in it. So it's these two things together which makes it a bit harder. So in fact, it's a bit more complex altogether, but the idea is that if you have a Feebly interacting particle around, and if it has pretty large couplings, which makes it a bit hard to see, but okay, hard to hide, sorry, then you can try to actually make as if this data-driven approach actually would need it to include new physics contribution both into this kind of diagrams here, which leads to an indirect effect because it will change the hadronic vacuum polarization measurements if you want. And it will also give you like a direct loop-induced contribution, both at the same time.
Right, okay.
So we found that in some cases, in fact, you can have like a 1/4, 3/4 effect. And the idea is that using that thing, you can actually solve both some internal constraints between data-driven and lattice, and also push it a bit more toward getting your data.
It's very subtle, but
it's very subtle, yes, honestly, and it's pretty hard to do also. But I mean, we're in a bit of a weird situation here because we have 3 sigma, 4 sigmas anomaly everywhere in those measurements. So the nice bits of those objects that basically you can solve it. You don't solve everything. I mean, you put new physics in, but once you put new physics to get most of the anomaly, it can also be used to make the data-driven and the lattice match, basically.
And have you been able to, so can I ask a question right now as we are just on the topic? Have you been able to, for a specific fifth model, to correct the luminosity and then find the vacuum polarization that cancels the anomaly?
Yes, actually, it's exactly the idea model that I presented. So you know the model also.
Okay.
So there is an interest that there is a regime in which so the actual process that we used was not exactly this, but E plus E minus to V, and then V will decay into Chi1, Chi2. That's the idea model, right? But Chi2 will want to decay again into this way, E mu.
Okay.
So you have some missing energy here, but what is very important that the experimental calibration are not very good at tracking that. So because of the problem is that this process can have initial state radiation, which is lost in the beam, meaning that you can in principle have missing energy in these processes also. So this process is in fact quite effective in completely mimicking this one there in a certain part of the parameter space, basically.
Amazing. Okay.
So altogether, but it's a bit hard because it requires coupling significantly larger than what I showed you before. And this occurs because, let me show you. Oops. Okay. So you see here, most of the things stops at 10 to the minus 3, right? In fact, when you have these types of final states, it's significantly harder, experimentally speaking, to probe it because you see that there is no resonance at all. You just have three-body decay, so it's not a bump. On top of that, you have missing energy. So it's extremely hard experimentally to see that. And that enables you to push the limits by an order of magnitudes higher. Meaning that even if, let's say, oops, exactly, there. So you see here it's excluded, but if you push it by 1 order of magnitude, it's not.
Okay.
So in fact, you can still rescue the pure dark photon search scenario in this idea model I showed you before.
Okay.
which has motivation in dark matter on top of it, so it's not that ugly altogether.
Oh.
Okay,
Thanks
so I think that's.
details. I mean, that was enlightening. I was saying thank you for the details of.
Yes, no, that's my pleasure. Okay, so I think that we can close the lecture here. It's been 2 hours. So, yeah.
Wow.
So, do you have any questions on whatever we did before?
For me, I'm good, but I don't know if.
Yeah, we had quite a lot of questions already. Thanks a lot.
No, it's okay. Thank you.
Thanks a lot for coming, Corinne.